Hello, welcome to the channel E square P. Here today we will solve the first question of chapter 1 from Goldstein. The question reads as that we show that for a single particle with constant mass, the equation of motion implies the following differential equation for kinetic energy. This is the equation that we have to prove where the mass is constant, and while if the mass varies, the corresponding differential equation would be this. Alright, so what we are given a single particle and the mass is constant, that is m. So, and we have to prove the equation of motion is full derivative of kinetic energy equals to dot product of force and velocity. Okay, so from Newton's laws of motion, we know the equation of motion is change in momentum equals to force. So F equals to P dot, and where P dot can be written as d by dt of P vector, that is the momentum vector. Here P is momentum vector. Okay, and what by the definition of momentum it is described as mv. Okay, v is the velocity vector and m is our mass. Since now we'll multiply both the sides of the previous equation. I mean, we'll multiply by v over here and v over here. So what we get? This equation. And how do we get from this equation to this? It's like if you differentiate this term d by dt of half mv square, what we get is since m is constant, mass is constant and half is constant, we will get half m outside, then dv square by dt square, and get half m v to v dot. Okay, and we'll cancel the two. What we are remain with m v dot into v. What is v dot? V dot is nothing but acceleration, and mass into acceleration is nothing but force into v. So that's how we reach over there, and it's basically taking a velocity vector into differentiation. So it's a kind of reverse process of what we do into differentiation. Alright, now we denote half mv square as kinetic energy, and that's how we reach our final conclusion that the dot product of Fv equals to the total derivative of kinetic energy with respect to time. Okay, now we have to prove that if the mass varies, over here we have taken mass to be constant, alright, but if mass varies, the equation would come out different, and we'll see how that proceeds. Okay, we'll once again use the Newton's law to get the very basic equations of motion, and this time over here we have multiplied with v vector on both sides, but over here we'll multiply both sides by p vector, that is the momentum vector. Okay, and p dot p, okay, this is nothing but d by dt of p and to p, which if I take this momentum vector inside the derivative, it will be nothing by d by dt of half p dot square, p square. So that's how we reach this equation, and if I substitute the value of p bar, that is mv bar, and how I get p bar square, mv bar dot product with mv bar. Okay, and m is a scalar, though it's a varying quantity, but it's a scalar quantity, so I can take out m as m square and v dot v as v bar square. Okay, and how we represent t is nothing but half m v bar square. Alright, if we substitute that value in this equation, we get dot product of force and momentum is nothing but partial derivative of m and kinetic energy. So these are the relations that we really do not need to remember for any sort of calculation we might come across in future, but it's just a kind of revision to the mechanics that we have seen in the chapter 1 of Goldstein. Thank you.